When building compute shaders and visual simulations in Godot, it's surprisingly easy to lose performance during the last stages of the pipeline. You run a compute shader, it generates a texture, and then at the end of every frame, you copy the image data down to the CPU, just so Godot can upload it back to the GPU again for it to be drawn. In this episode of the Codex, we'll look at how to use the Texture2DRD class in the Godot game engine to get rid of that slow operation. If you're interested in learning how other parts of compute shaders fit together in Godot, check out our other videos on the channel. If you like what you see, don't forget to like and subscribe. So in Godot, a common and reasonable compute shader workflow often looks like this. You create an isolated local rendering device to run a compute shader on the GPU. The compute shader writes to some output image buffers. After each frame runs, the image data is read back to the CPU and converted into an image format that Godot can use. It's then assigned to a node or a sprite texture, which is finally sent back to the GPU for rendering. That round trip can be expensive. It forces synchronization, it requires an extra GPU to CPU to GPU transfer time during every frame, and it limits how far you can push complexity within each frame. If we could get rid of that image transfer, we should see a performance boost. So how do we display a GPU-generated texture directly, without copying the data to the CPU at all? To answer that, we'll need a clear picture of the pipeline we actually want. At a high level, the goal is to keep all of the data on the GPU, and we're going to use Godot's Texture2DRD feature to do that. A compute shader writes pixels into a texture. That texture stays on the GPU. Godot's main renderer samples and draws that same data. No readback to the CPU, no byte-to-image format conversions, and no per-frame re-uploads. One texture, two rules. First, it's the output image, written with the image store function inside the compute shader. And second, it's the sampled texture read by the Godot's renderer to draw to screen. None of the image data should pass through the CPU each frame. The CPU just links things together and schedules the work. So now that we know our starting point and we know where we want to go, let's look at how we'll implement this in our simulation projects. To make this work in Godot, we first have to choose the right rendering device. Recent versions of Godot give you two ways to access a rendering device. The first is to use a secondary renderer, create local rendering device. This creates a separate, isolated device. It's useful for offline compute, and it's often used in compute shaders like those found on the channel. But its resources are invisible to Godot's main renderer, and the data has to be sent back to the CPU before it can be drawn. The second way is using the main renderer, getRenderingDevice. This is the default rendering device, the one Godot itself uses to draw the frame and all of the nodes in the scene tree. And if a texture needs to appear on the screen, it has to be created on that default rendering device. That's an important point. If you use a local rendering device like you see in most compute shader examples, there's no way to display the texture without copying the data back to the CPU. So for GPU-only rendering, the main rendering device is pretty much required. Our existing code wouldn't change much yet, we'd just make it use the getRenderingDevice function. But later in the video, we'll see how to properly interact with Godot's rendering thread. Okay, now that we have the right rendering device, we need a way to expose its textures to the Godot scene system. Texture2DRD is a bridge between Godot's scene system and the low-level rendering code. It doesn't store pixels, it doesn't upload data, it simply points to a texture that already exists on the GPU device. Internally, it holds a single thing, a texture resource ID created by the rendering device. Once that resource ID is assigned to a GPU texture, you can use the Texture2DRD pretty much anywhere a normal texture can be used in Godot, like on a texture rect or for a sprite. This Texture2DRD object is how we'll make the image appear on screen without being transferred to the CPU. But this method will only work if the texture itself is also created on the main rendering device with the correct settings. Let's look at the texture settings in more detail. The texture we create will serve two purposes. It's writable from within a compute shader, and it's readable by the Godot main renderer. That means the texture format and usage flags that we set both inside the shader and within Godot will be important. The image format in Godot needs to match the image type that the shader is going to write to. For example, in GLSL, we're using the RGBA 32-bit float type. So we'll map that to the same format in Godot, the RGBA single float format. Matching the format for the texture is important, but so are the usage flags we need to apply to that texture. The flags should include the storage usage bit, so we can use the image store function in our compute shader, and the sampling usage bit, so Godot can sample the texture during scene rendering. If either one is missing, the pipeline will probably break. You may need additional flags depending on your needs, but those two are the bare minimum. Then, once the texture is created using the right format and flags, we keep its resource ID. That resource ID becomes the link between the compute side and the rendering side. Okay, let's see how to actually bind that texture into a compute shader. On the shader side, our texture is declared as an image 2D uniform. On the Godot side, this means we'll be creating a uniform of type image and attaching the Texture2DRD's resource ID to it. And from this point on, the compute shader can write pixels directly into that texture using the image store function. No intermediate conversions required, and no need to pull the texture to the CPU each frame. But still, there's another thing we need to do for this to all work correctly. I mentioned before that all rendering device operations should be run on the rendering thread. This includes things like creating the textures and the RIDs, updating buffers, and dispatching the compute shader kernels. If you perform these actions from the main thread, where all scene processing occurs, it will work fine in most cases, but you may eventually hit crashes or undefined behavior, which can be very hard to troubleshoot. Godot provides a workable solution to this problem. We'll use the rendering server's call-on-render-thread function. We can use it to schedule the initial setup work and the per-frame compute work, both from the main thread, but have them execute on the rendering thread. The main thread stays focused on input and scene logic within Godot. The rendering thread handles scene drawing and GPU execution. This separation isn't optional as far as I could tell. I think it's just part of working this deep within the engine. This also means we no longer need to manually submit or synchronize our rendering device, since Godot will handle it for us automatically in the rendering thread. So we'll comment out those lines. Anyway, with the compute processes now running on the rendering thread, we can finally display the results to screen. Displaying the GPU texture is one of the easier parts to this. We already assigned our texture resource ID to the Texture2DRD, so now we just need to assign that Texture2DRD to a normal Godot node like a sprite or a texture rect. We're using a texture rect node here, so we'll use its texture property to make the final connection. Every frame, the Godot renderer samples the exact same texture that the compute shader just wrote to. There aren't any conversion steps. The update is automatic since they're running on the same rendering device. Nothing needs to be copied or refreshed manually, which leads directly to the biggest performance benefit. At this point, everything is wired together. So let's look at what this setup actually buys us, and what tends to break if it's not done carefully. The compute shader writes into a texture. The texture stays on the GPU, and Godot's renderer samples it directly every frame. There's no CPU readback, no uploading of data back to the GPU just to draw it. That's the real payoff. You remove that major synchronization point from the end of the frame loop, which lets performance scale more cleanly as complexity increases. Large grids, denser fields, and GPU-driven simulations become more practical in real time. But this setup is also pretty strict. When it breaks, it usually breaks for predictable reasons. Using a local rendering device instead of the main one. Forgetting the sampling usage flag on the texture. Calling rendering device functions outside of the rendering thread. Moving too much logic into the rendering thread. And not clearing RIDs after they're no longer needed. Any one of those can quietly break the pipeline. CPU texture readbacks can be useful for debugging, and sometimes they're just required for your workflow. But they shouldn't be part of the end solution if high performance is the goal. When everything lines up, though, the result is exactly what we want. GPU-generated image data staying on the GPU from compute to display. When you remove CPU readback from the loop, more performance suddenly becomes available. So use this method when the GPU is the source of truth, you don't need the data on the CPU for other reasons, and you want to improve frame times by not moving that data to the CPU just to have to send it back to the GPU every frame. I highly recommend this solution, but ultimately, if you're concerned with this level of performance, you'll want to benchmark several different solutions and use what makes most sense for your specific needs. I hope this video gives you another tool in your toolkit for building GPU-driven systems in Godot. If you have questions or comments, let me know. Thanks for watching the Pathfinder's Codex, and as always, never stop trying new things.